7.4 Lesson 1, Finding Arc Length. Our objectives for today are 1. You will know the definition of arc length, and 2. You will be able to evaluate the definite integral from the definition of arc length to find arc length. So vocabulary today, a smooth curve. That basically means that you don't have any sharp corners, and then arc length. This is the definition of arc length. It's a definite integral, and we will see tomorrow how we come up with this. Today we're going to use it, but I would like to just say a couple of things to preview what we will be doing tomorrow to come up with this definite integral that gives us the length of an arc on a curve. The problem is as follows. Suppose you have the graph here that you see. It's the graph, it's a parabola, and let's say you wanted to find the length of this arc that I will trace out using green ink from x is equal to 0 to x is equal to 10. So let's say you wanted to find the length of this arc. The problem is that there's not any formula from geometry that would allow you to do that. So what you can do is you can approximate the length of this arc. For example, by drawing one line segment, as you see here. That would be a terrible approximation, but it's easy to find the length of this line segment. You can use the distance formula, knowing the coordinates of the two endpoints, and using the distance formula, you can find the length of this line segment. Of course, you can get a better approximation by using more line segments. For example, you could have two line segments, maybe one here and maybe one here. And if you find the lengths of those two line segments and add them, that would be a better approximation than what you saw earlier. Now, if you wanted something even better, you could have maybe 5 line segments. You could have, let me see if I can draw these line segments nicely. You could have one, let me use a different color so it shows up a little bit better, maybe blue. So you could have one here. So line segment, let's say line segment 1. You could have another one here that I'll use green for. Line segment 2. You could have a third one that I'll use gold for. Line segment 3. You could have a fourth one that I'll use black for. Line segment 4. And you could have a fifth one that I will use blue for. Line segment 5. So you can see that when we use these 5 line segments and find the length of each line segment using the distance formula and add these 5 line segments together, that's going to be a pretty good approximation for the length of the arc. And the idea is the more line segments you have, the better the approximation. And tomorrow when we derive the definition of arc length, we're going to start with the distance formula, and then we're going to have a Riemann sum that represents the sum of the lengths of several line segments. And then we're going to take the limit of that Riemann sum as the width of each subinterval approaches 0. We will say as the norm of the partition approaches 0, and that's going to give us the definite integral. So we're going to get into the details of that tomorrow. But right now you have the conceptual idea of where the formula comes from. It comes from starting with the distance formula, forming a Riemann sum to find the sum of the lengths of n line segments, and then taking the limit of that Riemann sum to give us a definite integral. When you do all of that, this is what you come up with. And we're going to use that, and we're going to look at 3 problems. And then we will go over an example that's from the book, and you will work on that as a part of your homework. So let's look at the definition of arc length here. The definition of arc length states, let the function given by y is equal to f of x represent a smooth curve on the interval from a to b. The arc length of f between a and b is given by this definite integral. So what you have to do is you have to find the derivative of the function, square the derivative, and then that becomes a part of the radicand in the integrand, as you see written in the formula. Similarly, for a smooth curve given by x is equal to a function of y, the arc length of g between y is equal to c and y is equal to d is given by this definite integral. And of course, it's really the same as the first, but you just have integration with respect to y. So the limits of integration are y values. In the first one, you have integration with respect to x. So the limits of integration are x values. And of course, in the first one, you have the derivative of y with respect to x, and you're squaring it, and that goes in the radicand of the integrand. Here, in the second one, you have the derivative of x with respect to y. You're squaring that, and that goes in the radicand of the integrand. So now we're going to look at some examples using the definition of arc length. We'll look at 3 examples, and then we'll preview a 4th one, which is a part of your homework for tonight. So we begin with a pretty easy problem to do, and you'll see why this is easy. Find the arc length of the graph of the function over the given interval. So when you look at the graph that's given, you see that it's bolded from x is equal to 0 to x is equal to 1. So let's go back to the definition of arc length. S is equal to the definite integral from a to b, and the integrand is the square root of 1 plus f prime of x squared dx. So what would be the limits of integration for this particular problem? The limits of integration will be from x is equal to 0 to x is equal to 1. So we can start by writing the definite integral from 0 to 1, and you would have the square root of 1 plus. So now for this part of the integrand, what I need to do is I need to find the derivative of this function and then square it. So let's go ahead and do that over here. So the derivative of this function is found pretty easily. You would use the power rule for the first term. So you have 2/3, multiply that by 3/2, and then subtract 1 from the exponent. 3/2 minus 1 is going to be 1/2. And then you would take the derivative of the constant term, which is 0. So when you simplify, you get, you can see that 2/3 times 3/2 is 1. So you just have y prime is x to the 1/2. And then, of course, what do you have to do with the derivative? The integrand says take the square root of 1 plus the square of the derivative. So I have to now square the derivative. So the square of the derivative would be y prime squared, which is going to give me x to the 1/2 squared. And that's going to be x. You have the power of a power here, so you multiply the exponents. 1/2 times 2 is 1. So you just have x here. So how do you integrate? You can write that as 1 plus x to the 1/2 power and then you can use the power rule for integration. You would add 1 to the exponent and divide by the new exponent. So that would give you 1 plus x. 1/2 plus 1 is 3/2. Dividing by 3/2 will give you 2/3. And then you will use the fundamental theorem of calculus to complete the problem. So we evaluate the antiderivative at the upper and lower limits of integration to get what you see in the line above where I'm writing now. and you would just complete the problem by evaluating that numerical expression, and you would get your arc length. So if you wanted to leave the answer in exact form, you could write something like what you see here. If you wanted to come up with the decimal approximation, you can use a calculator and write the decimal approximation for the arc length. So here we have example 2, and the instructions are: find the arc length of the graph of y is equal to x cubed over 6 plus 1 over 2x on the interval from x is equal to 1/2 to x is equal to 2. And to help you see what the graph looks like, here's the figure from the textbook, the arc length of the graph of y on the interval from 1/2 to 2. So it's a little bit blurry, but you get the idea. This is the graph of the function, and here is the part for which we'd like to find arc length, from x is equal to 1/2 to x is equal to 2. So this is the arc length that we're looking for. And to find it, we're going to use the definition of arc length that we just learned today. And of course, just like you saw in the previous example, the first thing that you have to do is you have to find the derivative of the function, and then you have to square it, because you need to have that as a part of the integrand. It will be a part of the radicand in the integrand from the definition of arc length. So let's go through the process for doing that. So y prime, so you have y is equal to x cubed over 6 plus 1 over 2x, which you can write as 1/2 times x to the negative 1 power. And you just use the power rule to find the derivative. So using the power rule, you'll get 3 times x squared over 6. And then here you'll have negative 1/2 times x to the negative 2. So when you have y prime is equal to 3 over 6 is 1/2 x squared minus 1 over 2 times x squared. If you write x to the negative 2 in the denominator, that's what you have. And then you can factor out 1/2 from each term, and that will give you 1/2 times x squared minus 1 over x squared. And of course, that's what you see here. The next thing that we want to do is we want to square it. So we square the derivative. So when you square this, you're going to square both sides of this equation. And when you do that, 1/2 squared is 1/4, so that's where that comes from. And then to square this quantity, you have to multiply it by itself. So you see that here. And you have to do FOIL. So when you do FOIL, what do you get? You get x squared times x squared, which is x to the 4th. You get x squared times negative 1 over x squared, which is negative 1. And then you get x squared times negative 1 over x squared, which is negative 1. Negative 1 plus negative 1 is negative 2. And then you have negative 1 over x squared times negative 1 over x squared, which is positive 1 over x to the 4th. So that's how you get that particular line there. And the last thing that I did was I just distributed the 1/4 to each of these three terms, and that gives me 1/4 x to the 4th minus 2 over 4, which is minus 1/2, plus 1 over 4 x to the 4th. So now we're ready to go ahead and go back to the definition of arc length. Now that we have found the derivative of our function and we also squared it, we can just take this and substitute for the square of the derivative of our function that is a part of the radicand in the integrand. So you have the definite integral from x is equal to 1/2 to 2, and the integrand is, by the definition, the square root of 1 plus, so that's the 1 that's from the integrand, 1 plus the square of the derivative of the function. And of course, this is the square of the derivative of the function, so I bring that and write that in there. So the next thing that you want to do is you want to look at the integrand and you want to specifically look at the radicand and you want to simplify, you have 1 minus 1/2. 1 minus 1/2 is 1/2, which you can write as 2/4. So that's what I've done here. And the next step will be as follows. In the radicand, I have these three terms, and they have a common factor of 1/4. So I factor out 1/4 from each term, and when I factor out 1/4 from the first term, I'd be left with x to the 4th. When I factor out 1/4 from the second term, I'd be left with 2, and when I factor out 1/4 from the third term, I'd be left with 1 over x to the 4th. To go from this line to the next one, I'm using this property of nth roots. If you have the nth root of a product, you can write that as a product of the nth roots. So you can write what you have here in the integrand as the square root of 1/4, which is 1/2, times the square root of x to the 4th plus 2 times 1 over x to the 4th. Now, let me write that over here. So you have the square root of 1/4 times the square root of x to the 4th plus 2 plus 1 over x to the 4th. So how do I go from what you should have there to what I wrote here? I factored the part that I just circled in gold, and this particular expression, this trinomial, can be factored as the square of a binomial. So that's how we go from there to what I have circled in green here. So if you factor x to the 4th plus 2 plus 1 over x to the 4th, you will get the square of this binomial, x squared plus 1 over x squared squared. And if you want to verify that that is correct, you can do this. X squared plus 1 over x squared. You have x squared plus 1 over x squared. And when you multiply, x squared times x squared is x to the 4th. And then you have x squared times 1 over x squared, which is 1. And then you have 1 over x squared times x squared, which is 1. And 1 over x squared times 1 over x squared is 1 over x to the 4th. This is just to show you that, in fact, you can factor this trinomial as the square of a binomial. The question is, why would you want to do that? Because look at what we have now. You want to do that because you need to integrate. And it's hard to integrate something that looks like this, so you want to rewrite the integrand in an equivalent form that is easy to integrate. And the advantage of factoring this trinomial is now you have the square of a binomial and you're taking the square root of that. So squaring and taking the square root are inverse operations, so you're able to simplify to get this. And from here on out, it becomes easier to integrate. So this is where we left off. So to integrate here, you can first factor out the constant factor of 1/2. So I've done that. And you can also rewrite 1 over x squared as x to the negative 2 power. After doing that, it becomes pretty easy to integrate here. You're going to integrate term by term using the power rule for integration. So add 1 to the exponent here. So you have x to the 3rd over 3, and add 1 to the exponent here, and divide by the new exponent. So negative 2 plus 1 is negative 1, and divide by negative 1. And of course, we're using the fundamental theorem of calculus, so once you have the antiderivative, you want to evaluate that at the upper and lower limits of integration and subtract. One thing that you can do to help with that is to rewrite this power with a positive exponent in the denominator, And you see that I've done that. So having done all of that, we're at this step, and to complete the problem, you're going to substitute the upper and lower limits of integration for x, and when you do that, this is what you'll have, and you just do the arithmetic, and you will get the answer of 33/16. So here we have example 3, and the instructions are find the arc length of the graph of y minus 1 cubed is equal to x squared on the interval for 0 to 8, and these are x values. So if you look at the graph that's provided for this problem in the textbook, for example 3, this is the graph that you see. The arc length of the graph of y on the interval from x is equal to 0 to x is equal to 8. So notice that we have two endpoints. We have 0, 1, and we have 8, 5. And we're, of course, trying to find the length of this arc. And this arc is described by the rectangular equation, y minus 1 cubed is equal to x squared. Now, if you want to integrate with respect to y, you need to have x as a function of y. So we're going to go ahead and do that so that we have x as a function of y. So to get that, you're going to start with the given function, y minus 1 cubed is equal to x squared, and then you will solve for x. So you have x squared is equal to y minus 1 cubed, and all you have to do is take the positive and the negative square root. So you get x is equal to plus minus the square root of y minus 1 cubed. However, do you really need to take the positive and the negative square root? If you look at the graph, and if you look at the question, it says find the arc length of the graph on this interval for x, where x is greater than or equal to 0 and less than 8. And because this is the interval that we're interested in, where x is not negative, we only need to take the positive square root, because on this interval that we're interested in, x is not negative. So we're only going to take the positive square root, and we're going to have x as a function of y. So we have x is equal to the positive square root of y minus 1 cubed. So we have x as a function of y. And now that we have x as a function of y, we can use the definition of arc length where we will be integrating with respect to y. So in the previous two examples, we integrated with respect to x because we had y as a function of x. But in this example, we have x as a function of y, so we will integrate with respect to y. But when you do that, the limits of integration have to be y values, y coordinates. And to see what the limits of integration should be, you can look at the graph. That's one way of figuring out what the limits of integration should be. You can see that the two endpoints have ordered pairs 0, 1 and 8, 5. So when x is going from 0 to 8, y is going from 1 to 5. So those would be the limits of integration for our problem. And we've already solved for x as a function of y. And the reason why we took the positive square root was because of our interval for x not being negative. So the next thing that you need, just like in the previous examples, is you need to find the derivative of your function and square it. But of course, we're finding dx dy because we're finding the derivative of x with respect to y, as opposed to what we had done before, where we were finding dy dx. But you do it the same way, using the same differentiation rules that you've learned about. It's just that you'll have dx dy instead of dy dx. So when you do that, here's what you do. You're going to use the power rule, bring the exponent to the front, and subtract 1 from the exponent. So once you've done that, the next thing that you need to do is square your derivative, because that's a part of the definition of arc length. The integrand is the square root of 1 plus the square of the derivative of your function. So when you square both sides of this equation, you will get the square of dx dy is equal to the square of 3 over 2 is 9 over 4, and then you're going to square this quantity. When you square that quantity, you'll get y minus 1, because when you have y minus 1 to the 1/2 squared, you have the power of a power, and when you multiply the exponents, you'll just get y minus 1. So the square of the derivative is 9 over 4 times y minus 1. So what do you do now? You're going to go back to the definition of arc length. What we found is this particular part of the integrand. So we're going to write this in for that particular part of the integrand. And then you have the square root of 1 plus the square of the derivative, which we had found down here. So the next part that we need to do is we need to go ahead and simplify as much as we can so that we can actually do the integration by finding an antiderivative using the fundamental theorem of calculus. So we need to simplify the radicand. So how are we going to simplify the radicand? We can begin by distributing the 9/4 to the y and the -1. So that gives us this line. So the integrand is now the square root of 1 plus 9/4 y minus 9 over 4. And what you can do now is you can add 1 and -9/4, or subtract that. So 1, you can actually write 1 as 9 over 9. And then you have, actually no, you want to write 1 as 4 over 4 is 1 minus 9/4. So 4 minus 9 is -5, so you get -5/4, which is what you see here. And of course, you still have the 9/4 y that we didn't do anything with. So now we're over here. So how do we get to the next line? What are we doing? Well, you have for the integrand, this is what you have for the integrand, 9y over 4 minus 5 over 4. And this is what you have for the integrand. And for the radicand, you have a difference of two fractions with the common denominator of 4. So you can do 9y minus 5 over 4. And you're going to use this property of nth roots. If you have the nth root of a quotient, you can write that as a quotient of the nth roots. So now you're going to write this as the square root of 9y minus 5 over the square root of 4. And of course, the square root of 4 is just 2. So you can write this as 1/2 times the square root of 9y minus 4. And that's what I've done. And that allows me to factor out the constant factor of 1/2 from the integrand, leaving me with just the square root of 9y minus 5 for my integrand. And of course, I can write square root as raising to the 1/2 power, and that's what I've done here. To complete the problem, you need to find an antiderivative. So that's the fundamental theorem of calculus. You need to find an antiderivative of the integrand and evaluate at the upper and lower limits of integration and subtract. But of course, you could either find the antiderivative mentally, or you could do a formal U substitution. So some of you might be able to find the antiderivative mentally if you feel comfortable enough, or you can do a formal U substitution as I will show you. So if you wanted to do a formal U substitution, you would notice that the integrand is a composition of two functions, where the inside function is 9y minus 5. So we're going to let u be the inside function of 9y minus 5. Then the differential of u du would be equal to the derivative of 9y minus 5, which is 9, multiplied by the differential of y. So that's the definition of differentials. So now we have du is equal to 9 times dy. Divide both sides of the equation by 9, and you get 1/9 du is equal to dy. So this u substitution allows us to change variables. So this is called the change of variables step. And you'll notice that I'm sort of leaving the 1/2 out of my consideration now, because all I'm trying to do is find an antiderivative of this integrand, right? So I'll come back to the problem after I have found the antiderivative. But to find the antiderivative, I do this u substitution, I do my change of variables step, and this is now something that I know how to integrate. And that's the whole purpose of the u substitution. So now you have a power function, so you can integrate that using the power rule for integration. Add 1 to the exponent and divide by the new exponent of 3/2, which is the same as multiplying by 2/3. You would have the constant of integration. Of course, I have a factor of 1/9 that is outside, so I keep it there. All of that really is helpful for one reason. Now I know the antiderivative. So I'm not so concerned about the constant of integration, because what I wanted was the antiderivative, which would be 1/9 times 2/3 is going to be 2/27, and then multiplied by 9y minus 5 to the 3/2. That's my antiderivative. Now that I have the antiderivative, I can go back to what I had here, because that's the definite integral that I need to evaluate to find the arc length that I'm interested in. So now that I have the antiderivative, I can go to this line. So I evaluate the antiderivative at the upper and lower limits of integration of 5 and 1. And where is this 1/2 coming from? It's coming from over here. So now I just evaluate the antiderivative at the upper and lower limits of integration, substituting 5 for y and 1 for y and subtracting. And this is what you will have. And when you use your calculator, that's approximately 9.073 for the arc length. So this is example 4 from your textbook. Find the arc length of the graph of y is equal to natural log of x on the interval from x is equal to 0 to x is equal to pi/4, as shown in the figure. So of course, this is the definition of arc length, and you need to find the derivative of this function and square it. So you can write that in for the square of the derivative of the function as a part of the integrand. So how do you find the derivative of the function? That's what I'd like to mention. So remember from calculus AB that if you have the function natural log of x, the derivative of natural log of x is 1/x. So now you have a composition of two functions where the inside function is cosine. So when you find the derivative of y is equal to natural log of cosine x, you'll be using this differentiation rule along with the chain rule. So you get y prime is equal to 1/cosine x multiplied by the derivative with respect to x of cosine x, which is of course negative sine x. So that gives you negative sine x over cosine x for the derivative. And of course, sine over cosine is tangent, so that gives you negative tangent x for the derivative. So the derivative of the function is negative tangent x, and of course you see that over here. And for the integration rule to find arc length, you need to take the derivative of the function and square it. So when you square it, you're going to get the square of negative tangent x is tangent squared x. And that's what you see here. When you substitute that into the integration formula, you see that right there. So you have the square root of 1 plus tangent squared x dx on the interval from 0 to pi over 4. And how do you proceed from there? 1 plus tangent squared x is equal to secant squared x by a trigonometric identity. And the beautiful thing about that is you have the square root of secant squared x. So the square and the square root will undo each other, and there is an integration rule for secant x. So that's something that we learned in Calculus AB. So you have the antiderivative, evaluate that at the upper and lower limits of integration. And after you evaluate at the upper and lower limits of integration, this is the arc length that you find. So today we looked at the definition of arc length, and we used it to find arc length for the examples that we looked at. Tomorrow we're going to look at the derivation of the definition of arc length.